How to develop PLC programming? As already anticipated in the introductory chapter of the first part, in this second part of the course, we will introduce the PLC programming development environment called GXWorks 3. So we will start from the topic 8. We talk about retrocompatibility with the software projects made with the previous programming environments, so GXWorks 2 and the GX developer. For previous modular PLC, in particular the Q series. So we will see under what conditions it is possible to exploit GXWorks 3 to automatically convert an obsolete project into a new I-QR. We talk about programming languages, GXWorks 3 based on the EC 61.13.1.3 standard. We will see how to develop GXWorks 3. We will discover and know the elements that characterize the project 3. It will be shown how to make a hardware configuration in GXWorks 3. We will talk about memories that make up the PLC-R, then about the device and the label. The first differentiated in their turn in user device, therefore understood as programmable memories, REX and RPC, available from the system. So, for example, we will talk about M0, M1, M2, and so on to identify user device, to so on to identify user device. Therefore, system memories areas, but left programmable to the user. So this being already intrinsic to the system will not need a declaration of variables unlike labels as already known. We will also talk about system devices, so in this case special memory of system, bit and word, to which a univocal and non-mutable meaning is associated. So we will discover the SM for special bit memories and SD for special memory to word. We will talk about labels or tags, therefore user variables defined in PLC programming phase. When we will talk about the labels, we will differentiate local labels, therefore locally defined in a program container and therefore usable only from the same, and global labels, therefore globally defined in the project, which will be visible and usable from all the programs present in the project. We will also talk about module labels, therefore labels memories, and so on, associated with smart modules. And in this case, therefore, for this module label, the GXWorks 3 gives the possibility to add them, to integrate them into the project. Therefore, to make them own and precisely, this modules label will give us the possibility to program, therefore to interface in reading and writing. And writing, if required, clearly with the smart modules that are present in our configuration. So the labels can be of different nature. Therefore, we can differentiate different type of data for different labels. For example, we can define a label as a type of data, Boolean, therefore in bits, word, 16 bits, real, therefore a data of the type float, or a type of data as a string. Therefore, a label in the form of a string, let's say in point 20, we will see the types of execution of the programs. Therefore, we will see how the programs will be put into operation by the PLC. Therefore, scheduled on the basis of the type chosen by the user among those available by the PLC scheduler. So we will know these different types of execution. Finally, we introduce the GXWorks 3 which as said is the PLC programming software for IQ-R. Therefore, the object of this course, but also for IQF. For example, to program PLC compact PLC, such as FX5. The development environment is composed of several components. Some of them can be positioned as best they are appropriate. Therefore, the concept that we will see, the development environment is composed of many windows, most of which can be redimensioned, moved, placed that will inside their own work window. Therefore, from this point of view, let's say the system, the software gives the user the freedom to configure the environment based on its own level. Retrocompatibility. Projects created in GXWorks 2 can be opened and converted by I_QR in GXWorks 3. This function is supported practically for all CPU. So we will see how to follow a conversion in quotation marks automatic of project. Therefore, for Series Q, for example, programmed and designed with the GXWorks 2 development environment. In that case, we will go to project, open other format file. We will go to point to our project in GXWorks 2 format, and at the completion of this operation, we will find a project for a PLC, a project for a for a R120 CPU, not in BENS, but in this context, but in general, it is valid for all projects for Series R. The same project can be converted on different sides of CPU. We will see how to do it. The same operation. I am therefore referring to the discourse of retrocompatibility starting from project. In this case, developed in GX Developer. It isn't possible through the same operation, the same procedure. So open other format file. In that case, GX developer format. This operation isn't possible, so it does not go to a good end if not for project, therefore made in GX developer, referring to CPU Q safety. So in this context, for all other CPU, the project could first be converted in an intermediate step in GXWorks 2. Would be made first. Once the project is created, once the GXWorks 2 project is in the format, at this point it can be converted in the same way. So from GXWorks 2 to GXWorks 3. The programming languages attached and admitted by the environment. There are four that are ladder, ST, FBD, and SFC. New project creation. As done at the top in the navigation tab, at the top project new, we are asked, we open a pop-up where we are asked to indicate the family of the PLC. So in our case, IQ-R. We chose so an R CPU, and as type immediately after, we are asked to identify the type, so the sites, the exact model of the CPU with which we will interface. In this case, R4. You are also asked to specify the programming languages, the programming language for this first container, for this first program file that the system will create, following the key. However, it is good to say that the choice of programming language isn't binding. The software can be composed of program blocks written in the different available languages. So in addition to the first, we can go to add other programming containers in a different programming language from the first. So we can go to compose our project of more programs, for each of which we choose the appropriate programming language. The project tree of what is composed of different voices. The first one, module configuration. Here, the configuration of the system is graphically represented. We will go here to configure to perform the hardware configuration in our project. Following a folder, a part program, therefore referring to the part of programming under which the various execution modes are listed. So initial, scan, fixed, event, standby, no execution, and unregistered. We will see them better in detail later. What is important to say is that the programs and the program files, the program blocks, so our PO that we are going to write and design, and we are going to insert them into a particular folder. As in this case, the scans means that we are requiring that the program file will go into scan mode execution. Nothing prevents dragging, so by dragging and dropping, drag the program file or the PO towards another folder, such as fixed scan, because you choose to work in another execution mode. So in this case, we have a program file. This program file called standard program will go into scan mode because it was inserted under the scan folder. Next, we will find a part FB dedicated to the creation and containment in the project of any user function blocks and user functions. As for the PO, also the function blocks and the functions are composed in turn of two main components. So a local label dedicated to the introduction and definition of any local labels, referred in this case to this particular PO, and a program body, which will change its appearance according to the programming language. The same goes for the differences between function blocks and functions, and can be replicated for the content folder of the functions. Following a part of global label. Therefore, a global label folder. Here we will find, first of all, the container predisposed to the global system, where we users will eventually add those which are the global label. And then we will add the global labels that we have already created. There is no prohibition to create other containers, so more containers, maybe divide them and differentiate them also based on the topics, and clearly rename them. In addition to these users, the system can add in the project three M plus global. So we recognize the fact that it is in this case the system label from the M plus directory. We will see better later. We will see better an example. In the structured data type section, we can go to add to collect all the user data structures that we could go to define. Even that system could add some of its own. In the device section, I note in particular the device initial value section. We could add some components, therefore some tables, in fact containing the values that can be set referring to the device, the user device, in the CPU at the same time. So from here to program in a tabular form an initialization of device. In addition, in the project 3, part of system parameters. Parameter related to the CPU, or better, as soon as we open the GXWorks tree, module parameters. So here we will possibly configure the IP of our built-in Ethernet port, and in the module information section, this is populated gradually. That modules are added in hardware configuration. Before talking about the hardware configuration of the system, we see the main aspects that we have talked about so far. So I'm going to open an instance of GXWorks 3. As a first thing, we talked about retrocompatibility. If I had a project in GXWorks 2 format for a particular module in the PLC queue, and if I had to convert it, so if I had to convert my project to iQ-R, I could exploit this part, open then project, open other format file. I could go to point my GXWorks 2 project, and this. We will create a new project, and then we will see how to change the size of the CPU inside a project. To create a new project new, here we can see the various family of the PLC Mitsubishi. We go to point an R CPU. We choose in this case an R04. If we had an R04 and we could add to change the size of the CPU. We do have to clearly explain this choice in this phase. Now we continue to work with an R04. As a programming language, in this case, I choose FBD. Here the system asks me the module for an R04 CPU, which is our CPU that we want to integrate in the project. We have just created a project for R04. It tells me a module label not used, so I'm saying not to use module labels. In this case, the module intended as R04. We could change this setting, but maybe we do this operation then by hand. In the meantime, we confirm the not used. Okay, so not used. So we have created a first program file called main, whose program block is called prog PO. The program block is made up of local label that is presented in this way. So we'll come here to define local labels, in this case to this program, and a program body that is composed in this way because it is in FBD. We will see the red coloration function block. Fun, as we saw before, at the moment we have nothing. We could create function and function blocks. This will also be topic of the third part of the course. In the third part, we will see the container that the system creates by default, global, which is incidentally empty at this moment. In the part structure and data type, we could go to create structured data. Parameter are 0, then we can is also there is the global data, but then we move on the parameter of the R04 CPU. In particular, parameter module. Here, for example, we find in the basic setting part the IP address. So if we had to go to set to set an IP different from the factory one for our PLC, we could come here to write the IP address that we want to assign to the integrated Ethernet port. By default, the IP is 192.168.3.39. So this is the default EP. Now let's go for completeness to create another POW. Let's go to create another POW in a different program language. We can create this and maybe we call it automatic, and we go to create a new one. So a program block, maybe we call it manual. But let's go to the ST. An editor ST is presented in this way. Here we will clearly write our code in structured language. Back in FBD, it presents, we said, as a white analog sheet. Above, we find all the components typical for the FBD. So we can go to recreate our contacts in our coin. In this case, there are no assignations. So the question marks appear, and we come to the POW list and pick the integrated function of the system, more or less basic. For example, basic introduction, comparison, operation instructions, for example. We can choose a move. So we find the FBD block. We find the FBD blocks and the classic ladder rank for completeness. Again, in this case, we create a third, in this case, ladder. This is our program editor in ladder. But here now I create the program in a ladder language, and now it opens, and exactly this is for completeness our program in ladder. And now, in fact, in this window, I can use as I say, the shortcut to on the toolbar. We choose the contact. We can see, and okay, we have seen the three main languages for programming the PLC. Now I can with the shortcut I can go to project, and we created a project for R04. I be able to pass a larger size, so for example an R08. I will go to reconvert my project for R08, and in this mode, the project change module type, we will go to select another CPU. Clearly below the system, it warns us that yes, it will complete the conversion, but to pay attention to the device of the project. Hardware configuration of the system. As it is done, then we said let's go to the module configuration section. Here we will find on the right, in our element selection, we will find the list of all hardware components devices that we can add to our configuration. Finally, then once added, drag and drop, a parameter will be followed, right click, parameter fix, so that in fact the modules or that respective buffer memories will be digested by the system. And let's say the modules will definitely appear under the module information box. So within our project, we can also access the respective configurations, the individual configuration of the various modules. Now let's see how to make a hardware configuration. So let's go back to our project where we have an R04. Let's go to module configuration. At this moment, from R04 only the shape appears. Let's go. Let's go to select then our element selection, where before we found how to say access to the elementary function such as move. Now, being in module configuration, we find instead the list of our hardware components in the main. base, we choose what is the one that the main base. Let's say of the main unit, we choose one of the 5 slots. So we go to bring to drag the CPU to this point. In the first slot, now we have to add the power supply. For example, R61P and drag and drop. After after that, now we can, for example, add two input module. For example, we can add an RX 40 C7, and now we can add two of these module, and so after that we can add our master for a CC link IETSN network. So the network module RJ71 GN11 D2. Now after that right click, but after that we drag this module, right click, but before check system configuration. No error, so now we can do a parameter fix. So they are added under the information modules. These two digital inputs module. For the third, which is intelligent module, it asks if we want to add module label. At the moment, we continue to say no use, then we will see how to do manually, so how to add them manually. Okay, in front of the intelligent module of in particular network, this triangle could appear. Ask us to please execute an additional check of the parameter. So let's go into check parameter, and the check is completed. We exclude these signals of notification. Okay, to complete, I will show you how to complete the hardware configuration. In case there is an error 04 AN CPU. So now we create a new project. So we create a project, and after that we must return in module configuration. So project new. Now we selected our CPU. Now the project is being created. So we now we wait that okay, and we so now return in module configuration, in case the in module configuration, and drag and drop the base, the CPU. So after that the power supply, and now if we do a check, the system present an error. In fact, now we do the check, and an error is presented, because the task we to add the now we add the information module RJ71 EN71. So in CPU extension, we can add this module Ethernet più IE field. This E più IEF indicate that the first Ethernet port is standard Ethernet. Instead, the second is to manage an IE field at 1 gigabit. So now, after explain that, we can do a check, and Now we see that we will see that it is good, and we can close this project. In fact, drag and drop of this module. Okay. Now let's do a check, and in fact is totally is okay. So we can close this project. Okay, qua this the always the same advice, and okay. Uh, in fact, there are two memories. One fly, one does not. Interdistributed on the functionality. So in general, the data in the program memory are transferred from ROMs to RAM after a power on or a reset. So for the part of the programs, of the program. Another memory we always talk about RAM memory is the one related to the device and the labels. It is then partitioned and subdivided based on the fact that the device is talked about. So that it contains devices or labels, as well as the storage files, which is a portion of memory dedicated to particular file registers. This memory, then this subdivision can be repartitioned by the user. We will see how to do it in a moment. This is because the system based on the choice of CPU. So assuming you have an R04, the system provides certain areas and subdivides them in this way. So for example, for an R04, we will find 40 top words available by default to contain the devices. 32 keywords, let's say, 30 plus 2 to contain the labels, and 128 for the storage files. From the moment, for example, there is the need to increase the portion of memory for the labels, we will have to repartition. So go to remove, for example, from the device area, what we intend to add the label area. That is in the end the sum of these areas. However, in the case of an error 04 remains 200 keywords. So about 400 kbyte. The number of user points, seeing this other image, can be modified as well as the setting in the retention areas. What does it mean? In fact, in the device area part, so in this 40 keywords, those that we have identified as a user device are going to end up. We will see them better in a moment. And for these user devices, we can go to through the latch setting. We can also go to define the areas. We can go to distinguish between retentive and not. Looking at the other memories. This memory is used, so let's talk about data memory to archive the parameters files and the comment files. Function memory. This memory is used for special functionality, for example, log data. So how to say from the moment you choose as destination of the log data, the memory of the PLC, this data would go to the function memory part. CPU buffer memory. This memory is used by the internet function or in data communication between multiple CPU. So just as the smart modules have buffer memory, the CPU also has its own CPU buffer memory, which would use, for example, to exchange its own information with another CPU on the rack. Also, we say that the PLC-R gives us the possibility to integrate add an SD card for various functions. However, this memory is used, for example, to archive then CSV files created by program functions. In this case, SPF write and read for the copy of the values of the PLC device. So we can generate files, for example, text files, and bring them to SD card. So a copy of the PLC device data to a text file that is on SD card or reading. Okay. As for the devices, we were talking about users, system, and device. Here they are in this table, they are all reported. We will see, for example, we will see in a little while, a little better the user device part. I also note that there is a part then that we will call device of access to the module, or more generally, buffer memory. There is a type of address, then a device for the PLC identified with the UN, where N is the number of slots occupied. Then, for example, U1 slash G 1000 from the moment we wanted to go to program, then read or write the buffer memory 1000 of that particular module placed on slot 1, except that clearly there is the buffer memory 1000. But I want to highlight precisely what the device is to access directly to the buffer memory or to the buffer memory of smart modules. User devices, the main X we have already talked about now a little, even in the first part of the course. Refer to digital inputs and not only, but also general input nodes. Then in the code, in the program, we could use x0, x1, x2 to go to right. Then to input signals to right there is y, the same identical speech for the x, but reported to the y. So the outputs, internal relay, they are user devices. So M are bit memories used as auxiliary relays within the CPU module. All M are reset from the following operation, then following a power off or power on of the CPU, a reset or a clear latch. Then from the moment the latch is defined, we can use the latch. Then with this latch clear operation, we still go to clean them, reset them. Latch relays are of their own nature, so they differ from M for the fact that they are retentive. Link devices, devices that can be used for refresh data with any network modules present in the system. So, for example, in a TSN network, if we had to pull up map in the reading of bits and words, so bits and records from a TSN slave, we could lean on and use this device B for bit devices and W for information about 16-bit records. There are also timer type user devices, so a device that follows the time measurement from the moment the timer coil is activated. Relative contact is activated when the time elapsed reaches the set time. So there are different types of timer, retentive and not, 16-bit or long. So identified with the letter L, which are 32. They are also distinguished in low speed timer, high speed timer. This is based on the PLC instruction used. So the same timer can work in low speed or high speed. Out refers to a timer in low speed mode. Out H refers to a high speed timer. Counter, so device sorry, C and RC are devices that count the number of times that the input condition in the program are verified. This is adjusted by the counters through the instruction outC or outrc. Data register, widely used as well as the M, are memory areas that can be used in the program to process numerical data. It is still possible to address to bit each device of this type. So we can, for example, access D0.0, so to the first bit of the D0 register, or to the 16th through the D0.F instruction. Okay, let's see, for example, what it means to have to do with user device. For example, then as far as out first card is concerned, we know that it has 16 points, 16 inputs point, and 16 outputs point. In this case, it is a car with 16 digital inputs. It makes little sense to talk about outputs, but we can go eventually to read the 16 inputs related to this card. We will do it pointing to x0 in case you want to access the first input, or we can go to use, for example, then the 16, so xf, if we were to go and create a contact for the for another input of the second card. We have said the reason with the direction of the mean, we have 16 points, so the next will be in then the first of the second card will be in x1. Okay, so we are accessing directly to the user device. There is no need to define them, so there is no need to go to local label and declare in a label, because there are already recognized memories memorized by the system. In the same way, we could go to work, for example, with a number with a relay bit. So with for example, we can work with an M1, for example, or rather than, for example, we take move with this input transfer 54, for example, in for example the 2. So we transfer the 54 in the 2. Now we can also do this example. So as already said, the move in as we choose 54, so move 54 in the 2. Now let's look at the memory part. So let's go back to the CPU parameter memory device settings. Now here we find the areas we talked about before. So now we look at this. In fact, in particular, now we find that the area related to the device content, to the device content and the labels for an R04. We have 40 keywords as default, 128 for the file storage that we probably won't use, and 32 for the label part. If we go to the confirmation selection, it shows us what we saw earlier in the slide. So at this moment, our 200 keywords made available for the area device and label is divided. We could have the need, for example, to increase the device part, so from 40, for example, add keywords. This means removing one from somewhere else, but as long as the sum remains contained in our 200. This would lead no error. If otherwise we always went to add keywords in the area part to contain the device, and we will keep our 30 here, the error system which is telling us that we are exceeding the available area. So we return to our 40, okay. To our 40, okay. In this device area, what is what is ending us the memories are ending us our user device below device label and memory area device setting. We find precisely the occupation of the device area, so the occupation of the user device. So at this point of 40 keywords available, we are using about 13.4. So even now we can look here. So even here, if we keep those 38.4, here we would like to go to resides up to 38, our area, to make room for some other areas, as we said before. Also in this case, the system would recognize that there is something that does not return with the partition of the memory. So he's taking care of it. He needs to occupy 38.4. We give it to him to 38, so we could come here and reduce also the points the device. If they are not used, reduce part of the devices and then go to occupy less memory from the device part. So let's go back, restore the setting, and so we can go back into the initial condition. Let's go back to our section, and the part latch of the user device area, we can go to now to define. We can go to define respectively the range for retention or less. So for example, on the device, we would like to render the device from 0 to 500 retention. So M0 to M500 will be retention. The same can be replaced for other components, for other devices. So we can go back to the setting from other devices. This is the way to manage the retention, at least for what concerns the devices, not for the labels. We will come back soon to talk about labels. We go back to the setting. We go back a second before talking about the label on the part instead of system device. The system devices have an predetermined assignment, so they cannot be altered by the user. We are talking in particular of SM, so special bit devices, and special register devices. These are reading, the other in writing. For example, we find, I don't know, we see here the SM50, so it is a special relay that identifies the error reset state. Okay, so in this case, you're reading and writing, it means that we could, for example, command a CPU reset through this SM50 memory and read it. How to say the completion from the moment the bit is replaced by the system at 0. So in this case, I repeat in reading and writing. For example, we have the SM400. A bit is always on, and SM401 always off, and so on. We can also lean on this SM to generate clocks with different granularities. So for example, referring to the SM50, we could have the SM50 in the same way. So we could go and read the state of SM50 that we know to be. We know to be referred to the completion of the request for error clear of the CPU. So what is highlighted here, that on these memories, this device system, we don't need to make any statement because it is already integrated into the system. Now it can be useful when it comes to a device system to take this step from the moment you want to relay on this device systems in the programming phase. Go to the part of device comment, common device comment, and associate to our device a comment. Let's read the comment and bring them to the program. In this case, where possible, it reports the comment associated with the particular system memory. The label is a string of characters that identifies at least one location of memory in the PLC. It is possible to define the label by associating it in a univocal way to absolute devices, or leave the compiler the association. So in this case, we will talk about autosign. We are saying that it is possible in some way to link directly a device to a label. This can be done only in the case of global labels. So this is the first thing we have to do. The column synced in the declaration phase will be missing from the moment we are inside a local label container. There are two types of labels. So global labels, variables that can be used in the entire projects, so they are visible to everyone, and the local labels, variables that can be used only within the pool for which they have been defined. In this case, they will go into autosign because, as I said, there will be no direct link between device and label. As for the labels and the type of data now associated, we will go to associate the label with an elementary type of data, or a structured type of data, or even a label for the instance of a function block. However, as for the elementary data, we refer to this. So Boolean, so a bit word, 16-bit with a representation of 0 to 60 to 65, 535, double word, an integer, so from minus 32 768 to 32 767, so a bit used for the segment, double integer, real, and so on, up to, for example, define pointer, timer, and strings, the labels of any type. If they are, can be defined as array at their turn, so regardless of their type. They can be encapsulated in array format in a maximum array of 3 dimensions. For the labels, for each label, we will also define the class. So If it is a global variable, in the case which we have to deal with the global label or constant, a global constant, so to which we will associate the label in a unique way and not mutable. A value global retain, so they will be both global and retentive. So they will maintain their state in the event of shutdown of the PLC. As for the local, the class is increased in addition to defining local constant classic labels. So not constant retentive and other details, but referring to, for example, those of inputs referring to function block or function. So not to POW understood as a program container. Let's see what it means and how it is done to instantiate and create a label. So, for example, starting from the example local label, in this case, a local label for the program, the one defined automatic, so we can go to define a label people of Boolean type, a bit of simply type. Now we can also associate an initial value. In this case, we can, once defining the label people, we can go to use people clearly only within this program. So here people is recognized, but if we go to the program body of the manual, for example, people does not exist. So to define a global label, instead we go to the part of the container precisely global, and in this case we could, for example, create a global label start button, and also here of type we choose bit. If we go to the part show details, okay, we also see the direct assignment that is possible. We can do, for example, if we wanted to go on a panel operator Mitsubishi got, and in the part related to the got, let's say, in the project panel, this label have not been imported. So you work in short through absolute address, not symbolic. So here we could do an assign, for example, to M1. This to say that this link is not necessarily required by the system, but it depends little on the user that is being made of this label. In certain contexts, it may be necessary make an assignment associate a device to a label. As regards the types of execution of programs, we say that from the project tree, it is possible to visualize and set the program execution mode. So in our case, our programs are under the scan part. So these programs will go to scan mode execution. Let's see what it means. For example, as regards the scan, before talking about this, here it shows us how to access this to the settings where they come, let's say the information, the scheduling modes. The various program files are summarized, and then we can access the program settings. In the first type is the first type is the initial execution type. The programs within this type are executed for a single cycle on of the PLC scan. When the same goes from the stop pause operating state to the run state, so in this case the C-type programs, the C-type program initial comes into operation. C as well as B and A. So there are three initial type programs that are executed only at the first PLC scan. So this mode can be used to run an initialization required only to the power up. Scan execution type. These programs are executed once for each PLC cycles. Once the initial programs have been executed, which we say are the first to go into operation referring to the first scan, from the next they go into operation, and then the second one is the second scan where the program is set in the scan mode. So in this case there are three programs in a priority order based on the order established by this little button, this little window up down based on this execute order. The execution is given life, it is continuous between programs A, B, and C. In this case, A is priority over B, and in turn it is priority over C. Clearly, the longer the execution time required, so the more programs we write for what concerns these programs, the longer the PLC scan will be in terms of time. So clearly, the scan phase will depend on the time used by the PLC to run the various programs. Fixed scan execution type, unlike the previous ones, these programs are executed at the interrupt at a certain time interval. We talk about interrupt. So in addition to the settings, so the fact of bringing the programs inside the fixed scan folder in the project tree and setting the period. The periodicity with which you want to run the program, we need to run these programs. In addition to this, it is necessary to enable the interrupt with which the system works. This is done through the instruction AE. Now, so let's see this. For example, what would it mean if we wanted to create a fixed type program? Here we select the ST models. A program file has been created, main one, with the related program PO. This program will end in the execution in fixed scan because it was created under fixed scan. Let's go and see the settings. Here it would be missing before. Seeing the settings, I anticipate that the part of enable interrupt is missing. To make this program cycle, in the case we write M10 equal true, here maybe in the part of initial I could pass the system function to enable the interrupt. Otherwise, from the moment they are present, our fixed scans would not be executed. Here with this function, we have the program file. In this case, main one, if we go to the setting, CPU, if we go to the settings, CPU parameter, now before we see the AE for the enable, and so in the program body of the fixed scan can be executed. If we go to the CPU parameter, let's see something more. In particular, program settings, program setting detail setting. Here we are reported those that are our program files in execution. So we will find the main two in initial form, in initial type, main of scan type, and main one of fixed scan type. Therefore, the default is set to a second. But we could come here and and select our desired time interval in second unit or millisecond unit. Event programs can also be created where the event is defined by the user. If we see event execution type on bit, the program is executed if the bit is true, respecting obviously the execution order. In this mode, the programs are compiled by the software and downloaded from the CPU and saved in the memory, but are never followed by the PLC. A registered program under this folder, there are the programs that are not downloaded into the CPU and are not compiled by the compiler. So we could maybe use this section to move to park our program's object of compilation error. So in that case, by bringing them to the unregistered program, the compiler could not compile them. So we could go on with the censorship maybe of other programs. We said about priority order. So here we can go through this up and down to define the scanning priorities. The order in some way can also be established within a single program file. For example, in our program file mail, we have three programs: automatic, manual, maintenance. We could go to the program file settings, and at this point select here the execution order of the various program blocks. In fact, now we can see this. And here in general terms, we find the program file here, possibly from the moment a program file has more than one program block. So we could also determine the execution order for them going to work with this cursor, move up and move down. So for from the first to the last. So the first is more priority than in this case the third. And with this we finish the second part of the course. Thanks.